Good evening, students. My voice is audible.
If any problem, knock the door. Huh?
Good evening, students. I am going to explain the floating point representations. The floating point representations, that is the floating point the arithmetic operations. So, first one, what is meant by floating point number? The floating point number is it is a decimal number. It is consisting of the fraction parts. The floating point arithmetic operations. Arithmetic operations are addition, subtraction, multiplication, and division. The floating point arithmetic operations. So, in previous classes, we learned about the fixed point arithmetic operations. Now, we are going to learn about the floating point arithmetic operations. So, first of all, come to floating point arithmetic operations. The floating point number. So the floating point number is consisting of the two parts. The first part is called as a mantissa part. The first part is called as a mantissa part, and the second part is called as an exponent part. So coming to the example is 6132.739. So in this example, the starting integer digit is 6132 is the mantissa part, and what is meant by exponent means so before the decimal point. So in this, so how many digits after the decimal point are there? Four digits after the decimal point. So digits are 1, 2, 3, 4. So four digits after the decimal point is coming. Sorry for the inconvenience. Floating point arithmetic operations. The floating point arithmetic operations has two parts. The first part is called as a mantissa part and the second part is called as an exponent part. So coming to the example 6132.739. So in this example, the fraction is represented as, so you are removing the decimal digit and represent the total number. So here the total number is consisting of the 8 bits. So 8 digits. In this 8 digits, so it is the 7 1. Next, we are going to add the first one 0 0 6 1 3 2 7 3 9. So this is the fraction number. Next, coming to the exponent. Exponent is here before the here the decimal point is represented as after the 4 digits 6132 dot. So here the 4 digits. In this 4 digits, 4 digits. So the exponent value is represented as 4. It is the 4. Here, normally the general format for the floating point arithmetic operations are m into r to the power of e. Here, m is represented as mantissa and r is represented as radix. R is represented as radix and e is represented as exponent. The general form of floating point numbers is represented as m into r to the power of e. So here m is the mantissa, r is the radix and r base and e is the exponent. So here the radix and base is if the binary number the base value is 2. The binary number base value is 2. The binary number, hello. Yes, sir. Yes, sir. Record on this computer, sir. Okay, sir. Here, the binary number, coming to the general form of the floating point number is m into r to the power of e. So here, r is represented as radix. Radix are base. The base value for the binary numbers is 2 and the octal numbers is 8 and the decimal numbers is 10 and the hexadecimal numbers is 16. So these are the general format of the floating point numbers. Next, if the mantissa is a signed fixed point number and the exponent is the decimal point. These are the example. Next one. So in this previous one is the example for the decimal number. Next we are going to explain the floating point binary numbers. The floating point binary numbers is 1001.11. So here the represented as mantissa position. The mantissa, so the binary number is represented as 8 bits. It is represented as 8 bits. Here removing the dot. So the digits, how many digits after the decimal point is there? The 4 digits after the decimal point is there. So here the total number is represented as 01, 001 and 110. So it is the fraction number for the decimal point, fraction number for the binary numbers. Next one, exponent value. So here the decimal point is after the 4 digits. So after the 4 digits, here the exponent value will be 4. So in binary representation, the 4 value will be represented as 100. The value will be represented as 100. So it is the exponent value. So coming to the floating point representation for the binary numbers, example 1001.11. Here the plus sign is indicated. It is the positive number. So in this, the mantissa part, how to represent the mantissa part? The mantissa part is represented as, so mantissa part is represented as to removing the the decimal point, after removing the decimal point to represent the numbers 1, 0, 0, 1. Next, these numbers 1, 1, adding the 1, 1, 0. Here, the positive numbers plus the positive numbers are represented by the 0 bit. The positive numbers are represented by 0 and the negative numbers are represented by the 1 bit. So, you are representing the positive numbers and the negative numbers in the floating point arithmetic operations. The positive numbers are represented by the value is 0 and the negative numbers are represented by the value is 1. This is the binary representation for the floating point numbers. So here the decimal point is after the 4 digits. The exponent value will be 4. The 4 is represented in the binary formation is 100. Next one is normalization. So what is meant by normalization? Normalization means, example, if floating point numbers, the floating point is normalized. Normalization means to represent the numbers in fraction format, means integer format. So normalization means if the most significant digit is a mantissa is a 0. So the 0 is, it is not possible to perform in the any operations. So at the time you are normalizing the numbers. Normalization means to represent the number in a integer format. To represent the number in a integer format, that is called as a normalization. That is called as a normalization. So the normalization have the sum of the roots. So the floating point number is said to be normalized. So floating point number is said to be normalized if the most significant digit of the mantissa is a non-zero. The most significant bit is a non-zero, then you can performing the normalization. If the most, in this example 350, in this 350 is an example. Here 3 is a non-zero digit. So the non-zero digit, it is possible to normalize. It is possible to normalize number. So it is the integer number. It is understandable number. Using this number, you can performing the operations. So come to the second one is 00035. 00035. It is not normalized number. It is not normalized number. Why? Because so the most significant digits, all 3 digits are zeros. So in zeros, no, you can perform in the, no, you can, by using the zeros, you can get the result also 0. So how to normalize this number is, so here the 3 digits, before the 3 digits is, it is the zeros. The most significant 3 bits are zeros. You can remove the most significant 3 bits. So how to remove the most significant 3 bits? By using the shifting operations. By using the shifting operations, you can remove the digits. So here you can remove the 3 positions to the left. The shifting operations you can remove by 3 positions to the left and discard the result. Then you can get the value will be 35. You can get the value will be 35. So after the operation, it is represented as m into r to the power of e. M is 35 into 10 to the power of 3 is the result. So coming to the normalization. The normalization means the number is represented as a integer format. The number is represented as a fixed point number format or integer format. So how to represent the fixed point number format means the number is to be normalized. So by using the shifting operations to normalize the number. Coming to the first example 350. The 350 is a normalized number. So coming to the second one is the 00035. So in this, the most significant 3 bits is consisting of the zeros. Then you can remove the 3 bits. So how to remove the 3 bits? By using the shift left operation. So you can remove the shift left operations are used to remove the most significant digits, 3 digits. After removing the most significant digits, then you can represent it as 35 into 10 to the power of 3. Next, one more normalization rule is zero cannot be normalized. The zero number is cannot be normalized. Why? Because means the zero number value will be zero. So by using the zero, you cannot perform the any type of arithmetic operations. So the zero cannot be normalized. So which numbers are normalized means only the fraction numbers are normalized. How to normalize the fraction numbers means by using the shift left and the shift right operations. You can normalize the fraction numbers. So how to represent the zero number? The zero numbers are represented by all zeros at the mantissa part and all zeros at the exponent part. That is the zero number. The zero number is cannot be normalized because it does not have the non-zero digit. That is called as a zero number. Next one is arithmetic operations. You can perform the arithmetic operations in floating point numbers. So arithmetic operations are what type of arithmetic operations? Addition, subtraction, multiplication, and division. These are the 4 arithmetic operations. So in this the fixed point arithmetic operations are very easy and very simple. It is comparing to the floating point arithmetic operations. Floating point arithmetic operations. Why? Because means the floating point arithmetic operations, it requires the execution time is longer time. It executes the execution time is longer time, and it requires the more complex hardware. It requires more complex hardware. The floating point representation is also requires the scientific computations. It also requires the scientific computations because it representing the scaling problems. It representing the scaling problems. So coming to the arithmetic operations, the arithmetic operations with the fixed point numbers is it is very simple, and comparing to the floating point operations. The floating point operations are it is more complicated. The floating point operations are more complicated than the arithmetic operations than the fixed point numbers. Why? Because means it takes the longer execution time. It takes the longer execution time. It needs the extra hardware. It needs the extra hardware to perform the floating point operations. In floating point representations must be representing the scientific computations. In scientific computations, there are some scaling problems are occur. In computers. So how to solve the floating point operations means in computers how to solve the floating problems means by using the floating point problem is by using the subroutines. By using the subroutines programs. By using the subroutine programs, you can solve the floating point numbers. You can solve the floating point numbers. So here, example, you can perform in arithmetic operations. First, you can perform in the addition or subtraction. So how to perform in the addition or subtraction? To perform the addition or subtraction. So in this addition or subtraction, two numbers. So first, alignment of the radix point. Alignment of the radix point. Alignment of the radix point. The radix point means the exponent value. The exponent value must be equal to the two numbers. So we are performing the floating point addition or subtraction. In floating point addition or subtraction, here first alignment of the exponent value. The exponent value must be same. It is equal. Then you can performing the additions. The exponent value will be same. Then you can performing the additions. So in this example, so if it is a In this example, the fraction value is, the first one is 0.5372400 into 10 to the power of 2 plus 0.158 0040 zeros into 10 to the power of minus 1. So here look, to compare you can compare the exponent value. The first one exponent value will be 2 and the second one exponent value will be minus 1. So in this you can first alignment of the exponent value. The two exponent value will be must be equal. Then you can perform the addition or subtraction operations. So how to perform the addition or subtraction operations in floating point numbers? The first alignment of the exponent value. The exponent value will be same for the two numbers. Then you are going to perform the addition or subtraction operations. So here the first number exponent value will be 10 power 2 and the second number exponent value will be 10 power minus 1. So coming to, you can perform the, you can perform the exponent value will be equal. So how to performing the exponent value means, so here the first value is 0.5372400 into 10 to the power of 2. Here, what is the difference between the two exponent values? The difference is, the first one is 10 to the power of 2 and 10 to the power of 1 and 10 to the power of minus 1. So the values is three different values. So first number you can performing the first number can be by the shift left to the first number. After performing the shift left operation by the first number, then you can get the numbers is, 0.240000 10 to the power of minus 1. So here, after performing the shift left operations in first number, the most significant digits lost. The most significant digits are lost. So it is not preferable the first position, first point. Then you can go to the second one. Which one is the least exponent value? The least exponent value will be incremented by the most exponent value. This one is the preferable one. So here, to performing the additional subtraction operation, so you can comparing the exponent value. The exponent value will be same, then you can performing the addition or subtraction operations. The exponent value will be different, then you can performing the shifting operations. By using the shifting operations, you can equal the two exponent values. So coming to the second number, the first position is 3 bits to the left position and by the second by is 3 positions to the right position. So the second bit, you can performing the shifting operation by the first number. The 3 most significant digits are lost. So it is most significant digits is lost means you cannot get the exact result. So you need not to go to the first one. Which one is the preferable means, which one is the least significant, which one is the least exponent value. That exponent value will be incremented to the more exponent value. The second one is performing the shifting right. To perform the second value will be shift right. What is the second value? Second value is 1580. So you can performing the second value by the shift right. After performing the second value, the value is represented as, so 3 positions. You are shifting the 3 positions to the left. 3 positions, you can performing the 3 positions to the right side. So the 3 positions, the most significant 3 positions are represented as 000. After that, the number is 1580. So here the exponent values are same. Then you can performing the addition operation. Addition operation is, addition of the numbers is 5.5373980 into 10 to the power of 2. So this is the floating point addition operation. This is the floating point addition operation. So how to performing the floating point addition operation? So first you can comparing the exponent values. If the exponent values is equal, then you can perform the addition. If it is not equal, it is different one, then the least exponent value will be incremented. The least exponent value will be incremented to the most more exponent value. So in normalization addition, the normalization addition, it contains the overflow digit. It contains the overflow digits. So how to represent the overflow digit means the overflow digit will be neglected. The overflow digit will be neglected. Next, you can performing the subtraction operations. Then you can performing the subtraction operations. So how to performing the subtraction operations means, again you can comparing the two numbers. After comparing the two numbers, if the value will be, if the exponent value will be same, then you can perform the subtractions. So in this subtraction, the underflow value will be occurring. In arithmetic operations, in addition, what is the value will be occur? Overflow value will be occur. So in this overflow, overflow value will be occur. So how to overcome the overflow means, how to overcome the overflow? Shifting the some bits to the right, shifting some bits to the right and increment the value. That is the first one. So coming to the subtraction operation, the subtraction is also same as it is done. The subtraction also same as it is for the same procedure. What are the procedure you are followed in the arithmetic additions? The same operations with the same procedure will be followed in the subtraction. So you can subtract the digits. You can subtract the digits. So after subtraction, the underflow will be occur. After subtraction, the underflow will be occur. So in this underflow, to normalize the underflow values. So how to overcome the underflow values means, you are performing the shift left operations. You are performing the shift left operations and decremented by the exponent value. That is called as a normalization. So coming to the normalization means, you are representing the numbers in the fixed point representation. The floating point representation numbers, after performing the additions and subtractions, the result will be represented as a fixed point representations. So how to represent the fixed point representation? By performing the shift left or shift right operations, by using the shift left or shift right operations. Next, coming to the multiplication and division. Coming to the multiplication and division. So the multiplication and division operations, it does not require the alignment of the Montesa values. In addition subtraction, you can perform the alignment of the exponent values. So coming to the multiplication division, the alignment of the Montesa is not necessary. So how to performing the multiplication is, the multiplication is, it is performed by multiplying the two Montesas. Multiplying the two Montesa and adding the exponents values. What is meant by multiplication? The multiplication is multiply by the Montesas and add the exponent values. That is called as a multiplication. Coming to the division. So how to division do? The division is accomplished by, by dividing the Montesas. Dividing the Montesas and subtracting the exponents values. Dividing the Montesas and subtracting the exponent values. That is the procedure for your dividing the divisions. So how to performing the multiplication? Multiply the Montesas and add the exponent values. That is the procedure for the multiplication. Coming to the division, divide the Montesas and subtract the exponent values. So the operations performed with the exponents are, the first one is, you can performing the addition. Addition and subtraction is compare or increment. Compare and increment the alignment of the Montesas. So coming to the multiplication and division, you can performing the add or subtract operation. You can performing the add or subtract operations. Coming to the normalization. So how to performing the normalization? The normalization is performed. The normalization is performed by you can decrement or increment the exponent values. The number is represented in these in the form of fixed point representations. That is called as a normalizations. So what are the operations are performed with the exponents are in addition or subtraction. First one, compare and increment the exponent values. Based on the exponent values, we can align the multipliers. In coming to the multiplication and division, you can add or subtract the exponent values. Coming to the normalization means you can increment or decrement the exponent values. The number is represented as a fixed point representation. That is called as a normalization. So why the number is represented as a fixed point representation means using the fixed point representation you can perform the operations are very easy, and the execution time also takes the less amount of execution time. You can normalizing the numbers. The normalization numbers execution time will be less and it is very fast. It takes the less amount of computer subroutine programs. So before normalization is it is a risky one to representing the fraction numbers. It takes a longer amount of execution time is required. Next one, the exponent representations. The exponent values are represented by using a four methods. The first one is sign magnitude. The sign magnitude means it is the signs will be similar sign or different signs. Similar sign magnitude. It is a positive number or it is a negative number. It is represented by the sign magnitude numbers. In sign magnitude, 0 is represented as the positive sign and 1 is represented as a negative sign. So coming to the sign 2's complement. So how to performing the 2's complement? First you can performing the 1's complement. Then you can add the 1 to the least significant digit. You can get the 2's complement. So what is meant by 1's complement? 1's complement means you can change the bits from 0 to 1 or 1 to 0. So 1's complement means sign 1's complement. So how to performing the sign 1's complement numbers? How to perform means you can change the numbers from 0 to 1 or 1 to 0. So coming to the 2's complement. The 2's complement means first you can performing the 1's complement, then add 1 to the least significant bit. Then performing the addition operations, you can get the 2's complement. Then you can get the 2's complement. Next, last one is biased exponent value. So the biased exponent value means the biased exponent value. In this biased exponent, it is represent only positive numbers. It does not represent the negative numbers. That is called as a biased exponent values. In the biased exponent values, it represents the positive numbers means so it is need not required the bit is represented for the positive numbers. Biased exponent means in this biased exponent, so here in biased exponent, so coming to the biased exponent, so in this exponent value, the positive number is added to each exponent as the floating point numbers is formed. So it is internally all exponents are positive. That is called as a biased exponent values. The biased exponent values is represented as 2 power k minus 1 minus 1. So here the k value is represented as the number of bits in the exponent. The advantages of the biased numbers means it contains only positive numbers. The smallest possible biased exponent contains all zeros. The smallest possible biased components contains all zeros. That is called as the biased numbers. So the exponent representations are, the exponent values are represented by using the four methods. The first one is sign magnitude and the second one is sign 2's complement ones complement, and the last one is biased exponent. Sign magnitude means here they're representing the sign values. The sign values here, the zero value is represented for the positive value and 1 is represented for the negative value. Sign 2's complement means, so here you can here you can perform the ones complement. In ones complement, the one bit is added to the, in you are performing the ones complement. So what is meant by ones complement? You can change the 1 to 0 or 0 to 1. That is called as a. So after performing the sign ones complement, the least significant bit you can add the one value, then you can get the sign 2's complement. First representation is biased exponent representation. The biased exponent representations, here all the values will be represented as biased exponent means all the numbers are represented as a positive numbers. That is called as a biased exponent value. So it is the advantages of the biased numbers. It contains only positive numbers. Here, the smallest possible biased exponents are contains all zeros. This is the advantages of the biased numbers. Next one. Next one, register configurations for the floating point numbers. So what are the registers and adders are used in the fixed point? The register configurations. The register configurations in the register configurations. What are the registers and adders are used in the fixed point arithmetics? Are fixed point arithmetic are used for processing the mantissa are the same in the floating point operations. The floating point operations. So coming to the diagram, the register organizations for the floating point operations is consisting of the three registers. The first register is VR register and AC register and QR registers. VR register, AC register and QR register. Three registers. Each registers are subdivided into two parts. Each registers are subdivided into two parts. The uppercase letters of the numbers is represented as the mantissa part. The uppercase is represented for the mantissa part and the lowercase is represented for the exponent part. So each floating point number has a mantissa is a signed magnitude representations. The signed magnitude representations and it is a biased exponent. The signed magnitude numbers, here the three registers now, BR, AC, QR. So in this BR, so here it is consisting of the two parts. The first one is the mantissa part and the second one is the exponent part. In this mantissa part, you can represent the signed bit. The signed bit will be, it is a BS. The signed bit is represented as BS. And coming to the AC register, the signed bit is represented as AS. So after performing the addition operations, addition or subtraction, after performing the addition or subtraction, the result will be stored in the AC register. After performing the addition or subtraction, the result will be stored in the AC register. In this AC register, it contains the two parts. The first one is A, it is the mantissa part, and the small a is represented as the exponent part. So in this capital A, it contains again two subparts. The first one is AS. The first one is AS. The AS is represented as sign magnitude and the A1 is represented, the AS is represented as sign magnitude and the A1 is represented as the most significant bit. normalized number. The most significant bit. After performing the addition or subtraction, the result will be after performing the operations, the most so it is the AC. Next, coming to the QR. Next, the QR is the register. Register is contains. So register configuration. The register configuration is consisting of the three registers BR, AC, and QR. In these three registers, that each register is divided into two parts. Each register is divided into two parts. The first part is Mantissa part and the second part is exponent part. Each Mantissa part it is representing the signed numbers, that is BS, AS, and QS. So in result is stored in the AC registers. Register AC. The result will be stored in AC. So in this AC register, the A1 value will be represented as the most significant digit. The most significant digit is must be a non-zero number. It is not a zero number. If it is, you can contain the zero performing the normalization operations. Normalization means you can performing the addition or subtract. You can performing the shift left or shift right operations. So here the parallel adder. Parallel adder. Parallel adder is used to you can use it to performing the addition operations for the Mandisas, and the result will be stored in the A register. Next, parallel adder and comparator. Comparator. So this can be used to performing the addition for the exponent value. The exponent value addition can be performed by using the parallel adder and comparator. Parallel adder and comparator. And the result will be stored stored in the stored in the stored in the small a in the small a register. Here in parallel adder comparator, the E bit is represented for the carry bit. The E is represented for the carry bit. So this is the register configurations. The most significant bit is always next one, addition and subtraction. So how to performing the addition and subtraction means, so first check for the zeros. First check for the zeros. If the two numbers is zero, the result will be zero, and any one of the numbers is zero. So the remaining number is also it is having the same. So that is the, for example, A B. Here A is equal to 0 and B is equal to 0. The result will be 0. If any one of the A is equal to 0 means the result will be B number. If the B is 0 means the result will be the A number. That is the check for zeros. Next one, the second one is align the Montisas. So align the Montisas means, so you can perform the exponent value must be equal. So after aligning the Montisas, next performing the additional subtract the Montisas. After performing the additional subtraction, next then normalize the result. These are the 4 steps you can perform in the addition or subtractions. So this is the flow chart for representing the addition or subtraction. So in this additional subtraction, add or subtract. Here the BR value. So the register value, BR register value will be 0. The BR register value will be 0 and the result will be 0. And if the BR is non-zero and the AC will be 0. If BR is non-zero and the AC value will be 0 and the result will be AC. So if the two numbers are 0, it is going to be terminated. If any one of the number is 0, then the result will be the next number is the positive number is the result. That is, if the two numbers are non-zero, then you can comparing the exponent value. You can comparing the exponent value. If the exponent sign magnitudes, if it is the first number is less than the B and it is equal to B and it is greater than the B. If the exponent value will be less than, then you can performing the shift right operations. If the exponent value will be greater, then you can performing the shift right operation. If the shift right to the a value. So here, if the two numbers are non-zero numbers, then you can perform the exponent comparisons, the exponent value comparisons. If the exponent value will be a is less than b, then you can performing the shift right by the a value. If the a is greater than b, you can performing the shift right by the b value. So after aligning the Montessors, then you can perform the add or subtract operations. The add or subtract operations are performed by using the exclusive OR operations, XOR operations. XOR operations as AS, XOR, BS, and AS, XOR, and BS operations in XOR operations. So it is performing the XOR operations. AX XOR of the A and B numbers. So first you can comparing the again. So after performing the operations, again you can performing the exponent values. If the exponent values will be similar or not. If the exponent values will be similar, it is 0, then the result will be added. If the exponent value will be different one, again you need to performing the normalizations of the resultant number. The first part is alignment of the Montessors. Alignment of the Montessors based on the explained value, you can align the Montessors. After that, performing the addition operations. After that, you can performing the addition operations. Then you can performing the normalizations. After. So how to perform the normalization? By using the shift left and shift right operations, you can performing the normalizations. So this is the addition and subtraction operations for the floating point numbers. So coming to the multiplication. So in multiplication means you can multiply the Montessors and add the exponent values. Here no comparisons of the exponents and alignments and Montessors are necessary. Okay, ma'am. So I will stop the today class. Then we are going to conduct the quiz. Then quiz session will be started. Thank you.